So in this section, we're going to talk about kinetic theory of gases. So we've gone from the idea where, oh look, it's like there's pressure, there's volume, there's temperature, and we've got to there's atoms moving in a box. And this is really, from a physics development point of view, quite important, because it's one of the first times people took like a theoretical model and worked it and got a mathematical answer, and then said, what does this answer mean from a physical point of view? So we like to include it in the textbooks because it's one of these first examples of using first principles to build a model, to then let run, and then see what we get. And then science, not just physics, but science relies on that more and more as time passes. We're always building models, we're always running them, we're always seeing what happens and saying, what's the answer? So that's really important. So we start off with this molecular idea, molecular model of ideal gases. So they said, we need to build a model, so what's it going to start off with? And we make some simplifying assumptions. Some are good simplifying assumptions, and some are not so good simplifying assumptions. So one of them is that the volume of the molecules is insignificant compared with the volume of the container. So if we took all the gas particles and shoved them in that corner, you wouldn't even notice it. So gases are mainly empty space. That's a good simplifying assumption. Because if that wasn't true, I'd have to subtract that volume away from the free volume. So let's just assume that volume is insignificant. That's a good simplifying assumption. And molecules follow rectilinear paths in random directions between collisions. So there's no preferred up or down or left or right. They bounce and go off in some direction. Again, makes things so that there's no preference for any axis, which means that what happens along one axis is the same as what happens along another axis, which is a great simplifying assumption. Molecules undergo elastic collisions. There's no kinetic energy loss when they collide. If there was, then you'd be generating heat all the time and the energy of the molecules would decrease. So again, a good simplifying assumption. And then the forces between molecules are negligible until they hit. So there's no long-range forces because they're complicated. There's no field effects. It's just like, I don't know you're there until I run into you. Again, a great simplifying assumption. And that all the molecules are identical. There's not a little variation, they're all the same. And we shove these things into our model. And what is our model like? Our model is like this. We have a box with a particle in it. And we say, let's give it a velocity and let's let it go. And we're not going to step through this because you don't need this. You just need the answer. But just to talk you through it real quick, we only deal in terms of the x direction. So we take the component in the x-axis of the mass, of the velocity, and we take the mass, and we imagine it bouncing against that front surface, because that's pressure. Pressure is when I bounce against the front surface, like that. Okay, so pressure is a force per unit area. So this particle hits that front surface with a force. The force is equal to my change in momentum. Is that not right? No, my rate of change of momentum, dp by dt, is equal to my force. So if I know my P is mv, so if I know my mass and my velocity and I know how it changes, it goes from that direction to that direction, I can work out my change in velocity. And I can say how long it takes to do that. It does that every time it bounces there and bounces back and bounces there and bounces back and bounces there and bounces back. I know how long it takes to go there and come back. So I know my delta T, I can find my force. If I know my force and I know the area, I know the pressure. If it works for one axis, it'll work for all three axes. If it works for one particle, it'll work for all particles. So that's all they do, because they step through it. It's really clever. And they end up with that expression, which is the same as that expression. P is equal to, I think that's the same expression, P is equal to 2/3 N over V times 1/2 mv squared. Now, let's look at this. This is one of those educational equations. You got a 2 on the top and a 2 on the bottom, and you're taught in grade school to cancel those things out. We don't cancel those things out because we get insight from it. 1/2 mv squared. What is 1/2 mv squared? kinetic energy. So this is saying pressure is proportional to kinetic energy. I better put Ke because K means degrees Kelvin. And you'd expect the more particles you have per unit volume times the kinetic energy, I get more pressure. So this equation actually is really easy to remember. It's kinetic energy times N over V. I'd expect N over V. If I have 5 molecules in a thing the size of the gymnasium, it's going to be less pressure than if I have 5 molecules in the thing the size of my thumbnail. So volume clearly must have an effect, and the number of molecules must have an effect. You can guess what those are. The only thing to remember on this is 2 over 3. That's the only thing that you could not guess. So you need to know this equation. And so we say a simple ideal gas contains 2 times 10 to the 6 particles, that's N is equal to, in a volume which equals 6 cubic meters.
So what is the N is what?
The number of particles. Okay. Oops. The number of particles. And the mass is 9 times 10 to the minus 9 kilograms. Minus 12 kilograms. I'm rushing. I've got to slow down because I will make mistakes. And V is equal to 4,000 meters per second. So did all those all right? 9 times 10 to the minus 12 is that guy, yes?
What's that other thing?
What's that one? That velocity. So P is equal to 2 over 3 N over V. Kinetic energy. 2 V's. Be careful about 2 V's. P is equal to 2 over 3. 2 times 10 to the 6. 6. A half. 9 times 10 to the minus 12. V squared. 4,000 squared. P is equal to 4,000 squared, enter, times 9 second EE to the minus 12, enter, times 0.5, enter, times 2 second EE to the 6, enter, divided by 6, enter, times 2, enter, divided by 3, enter. 16! What are the units going to be?
Power?
Oh. I'm going too fast. What we're trying to figure out? Pressure, and it's 19. Is that right? Some people say it's 19, but it's Pascal, whichever it is. Is it 19?
It says there.
Oh, well, yeah, but, you know, I wrote that as well. So, you know, take that with a grain of salt. So, not power. And so this is, like, really important. And I'm Russian, I agree. But, you know, it's like, it's easy to get these things confused. So if you just learn your equations the night before, it's going to be a disaster.
That's what we're going to do since we're doing this too. Like,
No, you've had these notes for a semester, okay? So
using the alphabet over and over in different.
yeah. Like shoes, you use them every day. It's like, you know, you don't get the left and the right confused. So, wonderful piece of physics. We just blew through it real quick. It's the way it goes. But if you have interest in it, Just look at it. It's a real tour de force. And in your engineering careers, you will make models and you will mathematically manipulate them and you will come up and say, what's the answer mean? And it will mean something. You know, later on, the ultimate with this was really Albert Einstein basically saying, okay, if there's no ether, then what do I have to do to velocity and time and mass to get this stuff to work? And he then worked the equations and said, this means that a clock will slow down by this amount as it goes faster, and it means that starlight will be bent by the sun. And, I mean, just outrageous things that people like me would say, that's obviously crazy, and dismiss him. And then experiment comes along and proves him right. And that's just like amazing. I mean, that's why he's so famous. You know, it's like he said the most outrageous thing and he was right. And he did it by building a mathematical model. He did it by not observation. He did it by saying, well, if this and this is true, then mathematically that's true. What does that mean in terms of physics? So it's an amazing, amazing thing. It takes a lot of guts to do that.
Since he proved it mathematically, now everybody took him serious?
No, not at all. When it was confirmed by experiment.
He built the experiment, or?
No, absolutely not. No, he was probably just. He probably knew people who did experiments, but he was very much a theoretician. Okay. So, if P equals, if that expression is true, we just decided it was and used it. And before we said that expression was true, remember PV equals N, KB is Boltzmann's constant times absolute temperature. Then, okay, I can substitute in. And I can say, well, then I'm going to get 2/3 N over V, a half M V squared times V, because this is P and multiply it by V. So I get that. And that must equal, PV equals NKBT. So I just substitute these two equations into each other. This enables me to isolate T. And so I end up with 2/3 KB times a half mv squared. And this is the justification for temperature reflects average Ke per particle. Notice the n's cancelled out. The n's cancelled out. So it's the average per particle. This equation I don't know, but I know this equation and I know this equation, so I can get this equation. So this is fair game. But I don't remember it. I figure it out, and it's easy enough. So, what? This reflects, T reflects average kinetic energy per particle. Okay. You're just winding me up, aren't you?
Oh no, I'm getting all confused, man.
We're rushing. So PV equals NKB times T, and P is equal to 2/3 N over V times a half mv squared. So if I put these guys into each other, 2/3 N over V times a half mv squared times, that's P times V, is equal to N KB times T. So T is going to equal 2/3. The n's cancelled away. What do we have? The v's cancel away. So mv squared. Now I'm getting myself, again, I'm rushing. So that cancels with that. So I get mv squared over 3 and that is over KB. So, what do I know? Ideal gas of helium at 100 degrees C. T,
1/2.
I'm sorry,
1/2. T equals is missing the 1.
Yeah, there's a
oh, I cancelled it out. No, I cancelled it there, didn't I? Oh, I did, but I put it back in, didn't I? Shame on me.
You can't cancel it out.
So that's right. We agreed on that? Is this one right? I'm going to go back and look. 2 over 3 times a half. Yeah, that's fine. Why is the V being cancelled? Because it's on the top there and it's on the top there. Remember, this is PV. So PV is equal to my P times my V. Cool. So my temperature is equal to 100 degrees C, which equals 373 Kelvin. And my mass of helium, my M, is equal to, oh man, 6.7 times 10 to the minus 24 grams, which equals 6.7 times 10 to the minus 27 kilograms. And show that the resulting gas has a speed of that. I'll find that answer. KB is equal to 1.4 times 10 to the minus 23 meters squared kilograms over seconds squared Kelvin. So T, show that the resulting gas has a speed of, so V is equal to, V squared is equal to 3T KB over M. So V is equal to the square root of 3T KB over M, which equals 3 times 373 times 6.7, oops, sorry, no, 1.4 times 10 to the minus 23 over 6.7 times 10 to the minus 27. So I'll get my calculator. 1.4 second EE minus 23, enter, times 373, enter, times 3, enter, divided by 6.7 second EE to the minus 27, enter, and then I say square root of that, so second square root, second answer, I'm going to get 1529. 1529. It's a velocity, so what's its units? Meters per second. Cool. What mathematical relationship links T, the particle's speed, temperature and speed in an ideal gas? So you look back and you go, oh look, temperature is proportional to V squared. Yeah. So if T is proportional to V squared, I'm going to get, what is it, quadratic. Yeah. Look back at your previous equation. T is equal to, look for V squared, look for V, you see it's squared. Links T with kinetic energy. Look back at your previous equation. Oh, that V squared was part of a half mv squared, which is my Ke. So T is proportional to Ke.
Or 1/2 mv squared.
Ke. So that means it's going to be linear for KE. That's a subtle thing going on there. When I break up my KE into V, it's a quadratic, but when I just keep my stuff together as KE, it comes to be a linear expression. I don't have time to go through this, but it's just basically either picking the graph or plotting the points. In this next bit, I'm gonna jump around quite a bit. Okay? What I want you to know is that if my temperature is given by this expression, which it was, then I can rearrange this and get the energy by itself. And so I find that my kinetic energy is equal to 3 over 2 kb times T. My kinetic energy is proportional to my temperature in absolute terms, absolute temperature. How many independent axes are there in a volume of gas? 3. So, is there any preferred axes in a volume of gas? It's all the same. So, we find it convenient to recognize the fact that that is, for each independent axis, we have a half kBt. So my energy is equal to 1/2 times Boltzmann's constant times the absolute temperature. That's how much energy is stored at any given temperature. As the temperature gets bigger, we store more energy. Now, they do weird things, because again, now they're like playing with models. So they say, suppose I only had a one-dimensional gas. Basically, imagine a gutter with a series of balls in that gutter. And you can put energy in, and how do they behave? They've only got 1 degree of freedom. They can only bounce into each other and bounce back. And what you'd find, and you can show it, what you'd find is that your energy would be 1/2 kb times T. You can model it. Then they say, well, supposing we had just a 2-dimensional gas, supposing we had a glass plate and a gap and a glass plate. So the gas can't go up and down, it can only go squared. How would this behave? And they find, yes, it behaves just as we expect. 2 times 1/2 kBt will give me my energy. And for a 3-dimensional gas, it's 3 times 1/2 kBt gives us my energy. So we tend to remember 1/2 kBt per degree of freedom. We call the x a degree of freedom because it's independent of y and z. We call z a degree of freedom because it's independent of x and y, and so on. So we have 3 degrees of freedom for this gas. And you work it out, and it works beautifully. Show that a particle of monatomic gas contains that much energy at 100 degrees C. 100 degrees C. So I say, okay, it's a 3-dimensional gas, so my energy is equal to 3 times 1/2 kBt. So this is 3 times 0.5 times K, 1.4 times 10 to the minus 23 times T, and T was 100, and it's in K already. So E is equal, did I forget my 2? No, it's that. Yes. Yes?
How did you know you got the 3 from?
Because it's a gas. It's not saying a 2-dimensional gas, or it's saying a 1-dimensional gas. It's a gas. So it's 1/2 kBt per degree of freedom. And a gas, 3-dimensional gas, is 3 degrees of freedom. Yeah? If I'd said, I wouldn't, but if I'd said a 2-dimensional gas, and in chemistry you might find they say a 2-dimensional gas, then you do 2 times 1/2 kBt. Yeah? Question or comment? No? Okay, cool. So, then we just got our calculator. And we go 3 times 0.5 times 1.4 second EE to the minus 23. enter, times 100. And I'm getting 2.1 times 10 to the minus 21 joules. So this is kind of nice. 1/2 kb, that's a constant, times T equals my energy for each degree of freedom. It works. You can check it, it works. Something as complicated as a gas becomes simple.
Sir, I get 1.4 times 10 to the negative 21.
I'm sorry, I get 2.1. So just check your numbers. Okay. I get 2.1 times 10 to the negative 21. Yep. Agreed? Yeah, got it. How much energy does the particle of monatomic gas have at 50 degrees C? Don't worry about that, we just did it. Now, this is where it gets a bit kind of interesting, but also we're going to skip a fair bit because, okay, I can store energy in a gas by changing its temperature. What did we call that thing in calorimetry that linked changes in temperature with heat? What was that term for so many joules per kilogram per degree C?
Specific heat.
Specific heat. So I should be able to work out the specific heat for a gas. Just like I could for a block of copper. I can work out the specific heat for a gas. There's a little bit of a complication. And that is the fact that I say to you, go to the lab and work out the specific heat for helium. And you want to set up the experiment. You have a Bunsen burner, thermometer, something to contain the gas. You've somehow masked the gas. And you come back to me with a very reasonable question, which is, do you want me to do this at constant pressure, or do you want me to do this at constant volume? Because if I do it at constant volume, then my pressure is going to go up. If I do it at constant pressure, my volume has to go up. So, you know, which way round do you want me to do this? And I say, I don't know, do it both ways. Because there are two reasonable numbers we will find useful. Specific heat at constant volume and specific heat at constant pressure. So for gases, we have two specific heats. The specific heat at constant volume is the energy required to change the temperature of the gas by 1 degree while by 1 degree. The specific heat at constant pressure is the energy required to raise the temperature of the gas by 1 degree while it's expanding. So at constant volume, you're just changing temperature. At constant pressure, you're changing temperature and you're expanding the gas into the room. When you expand a gas, mechanically, what would we call it? Work. So at constant volume, the heat is only been used to change temperature. And at constant pressure, it's been used to change temperature and do work. So which do you think will be bigger? The specific heat at constant volume, where you're only changing the temperature, or the specific heat at constant pressure, where you're changing the temperature and you're doing work? Which is going to be the bigger specific heat? It's going to be constant pressure is the biggest specific heat because you're doing two jobs. Okay, that's conceptual.
But I have a question. Doesn't the volume of the gas naturally increases while you're heating it up?
Not if I put it inside a pressure cooker. Yeah. I mean, that's yeah. If you have it free, then yeah, but you got it inside a pressure cooker. So, can we get a bit more mathematical? And we can. And what do we find? We should be able to mathematically predict the ratio of the specific heats. and we can. And we should be able to measure experimentally the ratio of the specific heats, and we do. And the question is, if we've got a good model, good experiment, we get the same answer. And we do for hydrogen, helium, neon, krypton, argon, all the inert gases. And it's not to do with their chemistry. It's to do with the fact that there's just a spherical ball of matter. Works great. So, well, let's try nitrogen. It's awful. It does not work out. Oxygen does not work out. I think actually I said hydrogen. I think hydrogen is H2, so it does not work out. Helium does, but hydrogen does not. What on earth is going on? How come that these things no longer match? And the answer is that our whole principle has been based on 1/2 kBt per degree of freedom, and we have 3 degrees of freedom because it's a gas. And for helium, neon, argon, there's 3 degrees of freedom because it's a monatomic gas. It's just a ball in a volume. But nitrogen is a dumbbell. I mean, that's the way it's shaped. And, well, you know what? I can store energy in a dumbbell by spinning it. We did rotational kinetic energy. I can store energy by spinning it. And you know what? There's 3 ways to spin it. I can spin it on an axis where I get a lot of energy storage, and I can spin it on another axis where I get a lot of energy storage. But on that third axis, there's really no energy storage because it's got a very small moment of inertia. Remember that? The mass is all near the turning axis. So a dumbbell has 2 axes where you get a lot of energy storage because the eye is big, and 1 axis where you get basically no energy storage because the eye is small. So these are, in theory, 3 new degrees of freedom, but because we can think about things, we know there's only 2 new degrees of freedom. That's 5 degrees of freedom. And even more so, I can take this dumbbell and I can oscillate it. And that oscillation involves kinetic energy and potential energy. 2 more degrees of freedom. So I end up with 3 for the translational stuff, just the gas is moving, and really 2 for the rotational stuff, potentially 3, but really 2. And then 2 for the vibrational stuff. So that's 3, 2, and 2. That's 7 degrees of freedom. So they try it. And what they find is this. At very high temperatures, that gas behaves like it's got 7 degrees of freedom. At very high temperatures. And then at medium temperatures, like room temperature, it behaves like it's only got 4 degrees of freedom. 5 degrees of freedom. And then at cold temperatures, minus 100, minus 200 degrees C, it behaves like it's only got 3 degrees of freedom. So it gets really interesting switching between behaviors. And this astounded people when they found it. And it was the first time they saw what we now recognize as quantum effects, where you either do this or that, and there's not much in between. You're not happy in between. So you either have translational motion with no rotation and no vibration. And at low temperatures, that's all you can afford. You don't have a little bit of rotation. It's there or it's not there. And then you go to these intermediate temperatures and you can afford the rotation, but you still can't afford the vibration. then you go to high temperatures. Now you can afford the vibration as well. So very kind of fascinating changes. Fundamental. I mean, this is like from a physics point of view, this is like historic and unprecedented and amazing. For us, it's just like, got to remember it's 3 and then it's 5 and then it's 7. It's like, that's where we come down to. What I can't justify to you, and maybe a chemist would know, I should talk to some of my chemistry friends, but I don't get why the degree of freedom for translation, I don't get why a translational degree of freedom stores exactly the same amount of energy as a rotational degree of freedom. They're different things. So I'm missing something about why is it half kBT even for a degree of vibration in vibration. I can't justify that. But I can visualize why, there's this sequence. So this slide tells you, oh look, when we heat a gas up at constant volume, there's no work done. And when we heat a gas up at constant pressure, there is work done. So we've got to take that into account. So that's what that slide tells you. And then it says, let's do some math on this. That's what that slide tells you. And then it says, oh, look, we find that there's a ratio of specific heats, 1.67. You don't need to know those numbers. You just need to know there is a ratio of specific heats. You've got to know which is bigger. Specific at constant volume, specific at constant pressure. That's a good question. And then you've got to know that for monatomic gases, there is a ratio, and it happens to be 1.6. But that if you look at more complicated gas molecules, you get these other numbers creeping in. And why? Why does it not work, apart from a very low temperature, for a diatomic gas? And the answer is that they have these degrees of freedom, so I'd like you to be able to name those degrees of freedom. I'd like to be able to tell me there are 3 rotational degrees of freedom, but one of them goes to 0. And that there are 2 vibrational degrees of freedom, and that there are 3 translational degrees of freedom. And at low temperature, the diatomic gas only has those 3. And round about room temperature, we've got those 6, but one of them is assumed 0. And at high temperature, we have those 8, but again, one of them was assumed 0. So I'd like you to be able to talk me through that. Okay? So it's quite conceptual. And this is the graph. It's highly exaggerated. The graph actually looks like this. It goes like that, and we go. And it's not sudden changes. It's very subtle, actually. Which, again, for me, I find that a little bit confusing. This is more over to the chemistry side. In practice, how many degrees of freedom does a monatomic, that single atom gas, have at very high temperatures? Monatomic. That's a beautiful trick question. Monatomic only has 3. You can't vibrate an atom. You can't rotate an atom. It's just no effect.
You can't really hold it either.
So holding a bunch of them. In practice, how many degrees of freedom does a diatomic gas have at very low temperature? 3. In practice, how many degrees of freedom does a diatomic gas have at room temperature? 5. So remember, room's 5, very high is 7, very low is 3. And don't fall into that trap. It's just monatomic is always 3 because you can't rotate it and you can't vibrate it. Well, you can, but it has no effect.
You said one of them was 7?
Pardon?
You said one of them was 7?
When you have high temperature diatomic gas, high temperature diatomic gas, you got 3 rotation, 3 translation, 3 rotation, but one of them goes to 0, so we end up with 2, and 2 vibration. Yeah?
I mean, like, of those 3 answers, you said one of them was going to 7. Yeah. That's degrees.
Which answer?
I don't know, I think you said
I said at the high temperature. Diatomic at high temperature. That's not asking about high temperature. That's asking about room temperature.
He's saying the first one is the high temperature.
Oh, that's monatomic.
That's monatomic, so it's only ever 3. I'm going to end to this little chapter on a sad note, and this is Boltzmann. So people, I must confess, I have a kind of love-hate relationship with Boltzmann. If you go through physics, you have to do a thing called statistical mechanics, which is the statistics of thermodynamics. And it's not a symmetrical distribution. You can get gas particles going incredibly fast, but they're not going to go less than 0. So when you get statistics which is non-symmetrical, you no longer have the bell curve, and so it starts getting mathematically more challenging. And so people end up doing statistical mechanics. At USF, it was like one of the last courses in the sequence, and it's challenging mathematically. It's just, so you go through this book and you really dig in deep. And if you do engineering, you'll do similar stuff. It's not like the math in physics is I don't think is that much harder than the math in engineering at all. It's just I think physics tends to be more varied, so I think you get stretched a lot more. I think with physics they tend to expect you to know it, whereas in engineering they kind of go, let me teach you this bit, you know. I always got the impression that engineering was like, let me show you how to do this the easy way, and physics was, can you figure out how to do this? So it's like, you know, but that's my own little, you know, psychology coming out, all my scars. So I remember hating Boltzmann with a passion. The guy had written basically science that I found incredibly hard. And then I learned about him, and he was basically, so he was a theoretician, mathematician really. Got involved in looking at the atomic nature of gases, worked out the statistical mechanics to do with how gases move, developed a whole bunch of math for it. He suffered from bouts of depression. He struggled with it most of his adult life. And if you've ever been around depression, it's one of those things where it comes on people, and frankly, you know, people tell them to shake themselves out of it. You know, hey, you know, go out and, you know, have a drink, just relax, and they can't. It's like it's a real problem. So people do suffer with it, and they've got to go on living. They've got to going to work and all that kind of stuff. And unfortunately, I think he was. Well, you can see he's relatively young, and he'd published his, you know, magnus opus. He'd published this theory, which was just ridiculed by the grand old men in the field. And he was just going through a real bad patch at the time, and he committed suicide. And then about 15 years later, the grand old men started saying, you know, that guy was actually right. And if he had lived, he would have become one of the most honored physics people out. He wouldn't have had to do another thing. I'm sure he'd have still been suffering with depression, but, you know, it caught him at a time. It was a bad thing that happened at a time when he was struggling. And man, you know, what he just done was remarkable. So I got a real soft spot for him, even though, you know, I still don't particularly remember my time I spent studying him with fondness. But what he's doing is he's trying to work out the number of gas particles with a certain velocity. And it's this. Okay? We don't need to know it. We don't need to know how it's derived. We just got to know. I want you to know it's there. And it's just an equation. And what he found, which is more important to me, is that when you get an asymmetrical distribution, then how do you talk about the typical velocity? You could talk about the most popular velocity, where the peak is. You could talk about the average or mean velocity. And you can talk about the root mean square velocity, and they are different. Whereas if it's a symmetrical, nice bell curve, they all lie on top of one another. I want you to know, if I asked you, could you draw that graph? Well, then hope it doesn't come up. You don't need to know the equations. You don't need to know that. That's all I want you to know. It is asymmetrical, and we have these different ways of measuring.
So
Just the graph. And I'll be happy with that. Cool. So let's stop there. Why don't we take a 5-minute break? Oh, we haven't got time for a 5-minute break.
Yeah.